Hey guys, so last time we talked about the addition rule, and in particular, what are some situations that affect our addition rule. So for example, the joint and disjoint, they give us two probability calculations. So this time we're going to be talking about the multiplication rule and what are some conditions we need to take into account in order to make sure that we apply the rule correctly. So let's go ahead and get started. So first things first, conditions. So like I mentioned before, we have these sort of subcategories of things we need to focus on. For example, joint and disjoint for addition rule. Now we're going to talk about conditions and conditional probabilities. So sometimes the occurrence of one event can have an effect on the likelihood of another event. This is called a conditional probability. And the notation of the probability of event A occurring given that event B has occurred, right? And so these are conditions in which something has already happened or something is assumed to have happened or will happen. How does that affect the probability of another event? Does that make sense? So the probability of event A occurring, or whatever the case may be, whatever the event is, given that this other event B has occurred. Does that make sense? So two events happening, one affects the probability of the other one happening as well. So it's given by the probability of A, and that little line is basically given B. So given that B has occurred, and I know it's kind of backwards, and statistics has a funny way of not always being straightforward with certain things, and this one is included. So they tell you the probability of A given B. So given that B has occurred, what's the probability of A? That's how kind of you should think about it, but when you read it, you say probability of event A given that event B has happened. So probability of event given event A occurring given that B occurred is given by the probability of A, and remember what that little upside down U was? Kind of looks like an A, right? And so it's basically AND, right? So it's like an upside down A goes with and bam. So probability of A and B divided by just the probability of B. So basic know is you're always dividing by the given. So in all these problems, you always find the probability of the two events happening at the same time divided by the one that you're saying, given this event, what's the probability of the other one happening? So A and B, or one event and two event, divided by the one that you're saying it's given by. So if two events do not affect each other's likelihood of occurring, they are considered independent. Oh, let me change that to red. So they're considered independent. So what does that basically mean? That means that the probability of A given B is still just the probability of A, right? Because no matter, even if B happened, A is not affected by it. A is just kind of chilling, doing its own thing. So it's kind of like if you have a boyfriend, here's your boyfriend doing some stuff, but you're so independent, right? You're an independent woman or boy, whatever you're into. And so your partner doesn't really affect what you do from there on out. So given B, so B is your X doing whatever they're doing, it doesn't affect you, and so you're still just A. Does that make sense? So probability of A is not affected by probability of B. That's what we consider independent. So now let's go ahead and apply this condition and kind of see if we can find a conditional probability. So what's the probability the person tests positive given that they did take this particular drug? So here we have what's called contingency table, and it basically has two factors and a bunch of numbers in between. So basically these numbers represent, so for example the 119, what would that represent? That's basically the number of people within our 300 sample who tested positive and also used the particular drug. Does that make sense? So that's basically how this table works. So we're looking at drug testing, whether they got a positive or negative result, and also did they take the drug or not. So let's go ahead and find the probability the person tests positive given that they did take the drug. I'm sorry. So probability that's positive given that yes, right? So yes means that they took the drug. Alrighty. So probability of positive given yes equals what? So probability of A given B, the top part is the intersection, right? We're looking at one and the other one happening at the same time. So probability of positive and yes Divided by what? What do we always divide by? It's right there. I wrote it down. Divide by the given, right? So we're given what? We're given that the person tested positive, right? I mean, I'm sorry. We're not given that. We're given that the person actually took the drug. So the probability of yes. Does that make sense? So 2 events occurring at the same time divided by the one that's given. So what's the probability of a person testing positive and also getting a yes? So we basically have to look at what's the total number of people, right? And then how many people tested positive and also took the drug. Does that make sense? So the people who tested positive and took the drug, how many of those were there out of our sample of 300? It's 119. Good job. So it's 119 of the people tested positive. Now, what's the probability of just being yes in general? So how many people fully did take a drug? So total, there was 119 that tested positive and took the drug, and then there were 3 that tested negative but took the drug. So total we have how many? 122 people that tested positive. That did take the drug. So that's 119 out of how many people? Out of 300, right? Because that's the probability of being positive and also having taken the drug. Because there's 119 people out of those 300 who fell in that condition. Now, the probability of yes is just 122 out of 300. Right? So once we work that out, we end up getting 119 over 122. And I'm going to leave it like that. It's fine. If you have to do it in a decimal place, just go ahead and write the number in. But I wanted to leave it like that in particular because I wanted to give you another way of calculating a given probability. So for example, if you're given the probability of A and B is this, the probability of A is this, the probability of B is this, you can find the given just by the formula. But if you're given this table in particular, this table is actually very easy to find a conditional probability. And let me show you how you would go ahead and do that. So basically, and this is not required. I'm just saying it's a very quick shortcut. You don't have to think about it very much. So what you tell yourself is you're going to cover everything but the given condition, right? So in this particular condition, our given was what? Given that the person did take the drug, right? So given yes. So given yes, you're going to block off, for lack of a better ability, you're basically going to block off mentally, or you can do it with your hand even. Sometimes I just put it on top of everything that doesn't matter. So basically, if you're saying something is given, then you only care about that particular condition. So you're going to block off no in total and just look at the yes condition. So now, given yes, that means you don't care about anything else. What's the probability that a person tests positive? So literally, your total sample now is 122. Probability of positive, given yes. So we have 122 people now, right? Because everything else, like I said, just cross it off from your mind. So we have 122 people in our sample. How many tested positive? 119. Crazy, right? So that's a simple way to do it, but that's only if you're given the table. So if you're given the table and they say given so-and-so, just block it off and you're good to go. Just work with those probabilities in the yes column. And then it could also work the other way, right? So we can also do horizontally. We would block off either positive or negative and just look at those numbers there. So we'll have a couple practice problems to reinforce some of this information. Let's go ahead and move on to the multiplication rule, which uses this idea of conditional probabilities and whether something is independent or dependent. So the multiplication rule applies when you're asked for the intersection. Remember intersection, aka the little upside down U or and, right? Events A and B. Of 2 events. So probability of A and B occurring is the probability of A times the probability of B given that A had occurred. Right? So basically we're saying A happened, now B may be affected by A. So we would say the probability of B given that A has already happened. Does Does that make sense? So kind of order matters a little bit. We want to make sure that we include the probability that's happening first, and then the second one, take into account, does B get affected by A or not? That's going to be the probability of B given A. So now if two events are independent, what can we say about probability of B given A? Basically, event B doesn't care about what happened with event A, right? If they're totally independent, they're totally separate, and therefore the probability of B given A, who cares what A did? B is independent of A. So it's still just the probability of B happening, whether A happened or not. Does that make sense? So the probability of A and B then turns into probability of A and B equals the probability of A times the probability of B. So this time our probability of B doesn't have that kind of conditional probability. It just is what it is, right? Because again, conditional probability only really matters if A affects B. If it doesn't, it's independent, we don't have to worry about that. Does that make sense? So it's probability of A times the probability of B given A, or if it's independent, probability of A times probability of B. Just like that. So now how do we define independent versus dependent events? And so here I have a couple of examples, but sometimes I put here, it's a matter of thinking critically about the events that you're talking about. So it's not always very clear cut, like these are all the possible ways you can have a dependent event, and these are all the possible ways you can have independent events. But we'll do a couple practice problems just to kind of help us hash out what does independent really mean and what does dependent really mean. So independence events, some very common ones that you might see in your books or practice problems that your teachers might give is the occurrences of diseases or disorders, right? So me having cancer should not affect the probability of you having cancer. Does that make sense? So diseases or disorders within people are independent events. And then also consecutive dice rolls or coin flips, because even if I roll a 6 on a die, right, does that affect my probability of rolling anything different on the next roll, right? There's still an equal probability of me having a 1, 2, 3, 4, 5, or 6. Doesn't really matter if I got a 6 the first time, right? And then also coin flips. So if I flip a coin and get heads, that's not going to change the probability of me getting heads again or tails the next time, right? It just matters about the flip. And so it's going to be a 50-50 chance every time. So those are independent events. Probabilities do not affect each other. Now some dependent events are pulling cards out of a deck or taking marbles out of a bag without replacement. So what do I mean by that? Basically, without replacement is I take an object and I don't put it back in, right? So why does that affect everything? Because let's say, for example, I pull out a queen, right? And now I ask you, what's the probability of me finding a queen, right? And this is out of a full deck. So the probability of me finding a queen the second time is what? How many queens would we have left? So there's 4 suits, right? So we would have basically 3 queens left. And then how many total cards do we have now? If I pulled one out without replacing it back in, I technically have 51, right? So me pulling out one card and not replacing it does affect the probability of the next one happening, because I basically changed up numbers now, right? I changed up what was my total number of cards, and I also changed up how many queens are in the deck. Now if I had replaced it and said, what's the probability of me finding a queen, replace it, and then find the queen again, it's the same probability, right? Because I still have 4 queens in my deck now if I put it back in, and I also still have 52 cards in my deck if I put it back in. Does that make sense? So that would be dependent, because the probability of me pulling a queen next time is affected by me pulling out a queen the first time and not putting it back in. Cool? Alright, so let's do some examples. So example 2, what's the probability of rolling a 4 on the first roll of a die, and then an odd number on the second roll? So dice rolls. If it's a fair dice, nothing's really happening. Are these events independent or dependent? They're going to be independent, because one dice roll does not affect the other, right? So rolling a 4 on the first roll. So the probability of rolling a 4, how many 4s are there? There's just 1, right? How many total numbers are there on a die? Basically the number of faces, there's 6. So that's the probability of rolling a first die. And let's go ahead and actually write it like this. Probability of 4 and then times the probability of odd, given that we rolled a 4. Now, do we need that last term to include the 4? No, right? So we can literally just say probability of 4 times the probability of getting an odd number on a roll. Why? Because, again, we're independent, right? So even if we rolled a 4 the first time, that's not going to affect my probability of rolling an odd number the second time. It's still going to be the same probability as if I didn't roll that 4 at all, right? So probability of rolling a 4, like we mentioned earlier, I kind of skipped this step, but there's 1 4 out of 6 faces times, now what's the probability of an odd number? The way you have to think about these is, looking for a 4, how many 4s are my set of outcomes, or my sample space, right? So way back in the beginning of this chapter, we talked about the sample space, all the possible outcomes, so that's the way you have to think about these. So there's 1 4 out of my 6 faces. Now, how many odd numbers are there? There's 1, 3, and 5, right? Those are 3 possibilities. How many total faces? 6, yes. So we end up getting 3 over 36, right? And that gives us 0.0833. Cool? Alright, so let's go and move on to example 3. So a bag contains 5 green marbles, 3 white, and 4 blue marbles. Find the probability that when drawing 2 marbles without replacement, the first is green and the second is white. Key word, without replacement. What does that tell me? Dependent events, right? So kind of referring back to this section here. Let me go ahead and highlight this, because this is a perfect example of how, if you're pulling out without replacement, things get basically bonkers. Cool. So find the probability that when drawing 2 marbles without replacement, the first is green, so probability of green, times the probability of what? Pulling a white, given that we pulled a green marble. Look at me putting a little slash. It's not a slash, it's a straight line. So white marble given that we pulled a green marble. So what's the probability of pulling a green marble? So again, think about the sample space, right? So how many green marbles are there at all? There's 5, good. So there's 5 green marbles. And now how many total marbles are there? So there's a total of 5, 3 is 8, and 4 is 12. Times, what's the probability of white given that we pulled a green? And think about this literally as if, okay, I pulled a green and I didn't put it back in there. How many whites do we have left? Pulled a green, there's still 3 whites in there, right? And then how many total marbles do we have left? Exactly. So we pulled a green one out and we didn't replace it in, right? So we're left with 11 marbles now. So we get 15 over 121, and that ends up giving us 0.6894. Cool? So that ends our brief discussion on the multiplication rule. And so we're going to go ahead and do some practice problems, and at the end we're going to do some advanced applications just to make sure that we're understanding how all these rules can be combined together, and also bringing back in complements, because complements help us a lot in some of the most difficult and tedious types of probability problems. So until next time, let's go ahead and work on practice problems.